Welcome to Lab Tutorial Video 3. We will cover the first half of Lab 2, the physical memory management part.
Before start, let me give an overview on what we will do in Lab 2 for accomplishing memory management in JAWS. After finishing Lab 1, we have our kernel in memory working with basic console device, and we are with physical memory. And then what we will do in Lab 2 are two things. We will manage physical memory first, and managing physical memory means like the reserving the physical memory for peripheral devices and allocate them for code and data, and also manage unused space of the physical memory and allocate that per system's request. And another part is like the managing the memory virtually, and like this includes like the creating virtual address mapping and also setting up the permission and applying access control to the memory. And let's get into the details of each part. Managing physical memory here means that how we reserve some part of this physical memory for peripheral devices such as console, network device, disk, or graphic card, etc. And for those devices, we need to reserve physical memory's address spaces for them. And reserving here means that we can't use these memory address area for other purpose. For example, storing data for video games or web browser, we cannot use these space. We can use another free space like this, but not for these address spaces because these are reserved for the peripheral devices. So we need to set this kind of the physical memory management in Lab 2. And there is a low memory under 1 megabyte, but please ignore this because this memory space is quite too small for these days, and then not that important in modern systems after the booting stage. This is important for the booting stage because like where BIOS stores its code, and then where the bootloader stores in the low memory, but after the booting stage, so we may ignore this part. And moreover, we have a loaded JAWS kernel during the boot stage, and we also need to allocate the physical memory to store that. Also here, allocate means that we will not use the same part of the memory for the other purpose other than storing kernel, because if we load an application data in here, then our kernel code will be removed or deleted, overwritten, then the system would fail to working because we will miss some of the part of the operating system kernel code. So we should not use this physical space other than storing just kernel. Furthermore, running the kernel and hardware, these are not the ultimate goal of the operating system. The goal is to run many more application programs in the operating systems. And to do that, we need to maintain the occupancy status of the physical memory. For example, which address spaces are reserved by devices, reserved by the kernel, and reserved by other program or application. And then we need to allocate free space, only the free spaces, upon the allocation request. And this is the first half of Lab 2. And for managing which part of the reserved and which part are used or free on the physical memory, and we will achieve this by implementing the following 5 functions. The second half is managing virtual memory. In this regard, we will implement a virtual to physical address mapping, and also we will implement the part for setting up the memory permission and applying access control to memory space. This is for bringing the 3 benefits of virtual memory to JAWS. Those benefits are transparency, efficiency, and protection. And for permission setup and access control part, these are for an application will never read the memory space allocated for other applications or operating system kernel. and we will learn how we can implement such things in a modern operating system for protection part of virtual memory. So from part 1 of Lab 2, Managing Physical Memory, we have finished the physical memory management, so you can regard the right side of this figure as the physical memory space. And then, as the first step of part 2, Managing Virtual Memory, we will implement the virtual address mappings. And an example of the virtual address mapping would be, instead of allocating the 16 kilobyte of memory, contiguous in physical like this, we can allocate it contiguously in virtual, for example, like this, and then we can allocate physical memory by page per 4 kilobyte page like this, and then create a mapping via page table to back these contiguous 16 kilobyte of virtual address space with disjoint 4 kilobyte pages in physical. So basically this is what we will do. So we previously used a contiguous physical memory space, but we will change it to use only the virtual memory space. But on the backs, under the hood, we will manage all this kind of the virtual to physical mapping to enable a contiguous virtual memory address space access. And in addition to having such a mapping, we will also implement the permission setup and access control part. This will be done as part of the implementing page table, and what it will be is like you can mention about the permission flag per each page. For example, read-only or read-writable per page granularity. By setting this, some part of this 16 kilobyte memory are read-only, while some other parts can be read-writable, and we will control such memory permissions in page granularity, which is 4 kilobyte. And then we will apply access control of memory. For example, for accessing kernel code, JOS Lab 1 maps the kernel to virtual address starting from F0000000, like this. And then what we would like to do is making this part of the kernel address readable for kernel but not accessible at all for user level, a non-administrative application level. And we will finish these by implementing the following 5 functions in exercise 4 and 5. And this part will be covered in next week's tutorial. So we will only cover like the part 1 of the tutorial in this tutorial video. And this is the high-level summary of Lab 2.
And let's start with covering exercise 1 for implementing 5 functions listed on the slide. Before start, please finish your Lab 1, and to start Lab 2, run the following commands: git checkout Lab 2 and git merge Lab 1. Let's take a look at how we can run the command. So before start, please finish your Lab 1 and run git checkout Lab 2. Then you can see the message that now you are in a new branch, Lab 2, and then run git merge. Git merge Lab 1. Then it will merge the Lab 2 part of the template for the JAWS and your implementation of Lab 1. So if you just close the bin editor, then Git will merge your implementation of the Lab 1 and the skeleton code for Lab 2. So after doing this, you can now start working on Lab 2. And let me share some tips for Lab 2. First, please read inc memlayout.h thoroughly. Inside the code, you can see the ASCII depicted the virtual memory layout of JAWS. In Lab 2, at the last part, in Part 3, you need to allocate the kernel part of memory. In doing this, please refer to this diagram in Inc memlayout.h, and I recommend you to open this file in one of your tmux pane when you implement the part 3 of lab 2. You need to refer to this kind of the values and permissions a lot, yeah, when you finishing lab 2. Next is about introducing a new tool. There is a tool called ctags, and this enables you to jump over the code for selected functions and variables in the Vim editor. To initialize tags with your code, you need to run the command ctags-R and dot at the top directory of JAWS. If you do that, you can hover across the files by pressing Control and right square bracket to take a look at the implementation of a function or definition of the variable, and you can get back to the original position by pressing Control T. Let me show you a demo starting in kern pmap.c. Now, let's run ctags-r dot first at the top directory of JAWS. And then you can run or you can open kern pmap.c, and then suppose you are curious about one of the function or macro here, roundup. Then what you need to do is to take a look at the implementation or definition of this macro roundup. You need to put the cursor at the name of the roundup and press Control and squared right bracket. Then the editor will automatically move to the file that contains the definition of the roundup, and the cursor will be exactly positioned at that position. And if you press Control T, then it will get back to the original position. So pressing Control and right squared bracket, it will get into the implementation, and you can nest it. For example, if we try Control right bracket on round down, then it will move to here. And to get back, Control T, so it gets back to the round up. And if I press Control T again, then it gets back to the original position. So not just for macro, we can use this for variables. For example, if you are curious about where the current pgdir, this variable, is defined, then put the cursor at here and press Control squared right bracket. Then it will find the definition of the variable. Also, if you are curious about where this function memset is defined, then press Control squared right bracket, then it will show the implementation of the memset. And then you can get back by pressing Control T. Yeah. So once you run ctags-r dot, then it will generate the file called the tags, and internally it stores all the names of the symbols and location of the line number in the file, and also which file the symbol resides in. And by using this file, our Vim editor can know that where the symbol is, and by pressing the Control and squared right bracket or pressing Control T, then the editor can automatically open the file for you and get back to the original position. Let's start about exercise 1. The first task is implementing bootlock. Please note that our code contains lots of commands, and those inline commands are there for helping you understand what is the purpose of writing this function, and also guide you to the right way to finish the lab assignment. So please read comments thoroughly and follow the guidance written in the code as well as in our lab assignment webpage. And the bootlock is an allocator for physical memory, and we will use this function only for bootstrapping the virtual memory system in JAWS. The real allocator for JAWS is pagealloc, which we will implement later, and we will not use this function bootlock other than the first part of lab 2. And you can take a look at the description of the function in the comments of the code, and from the description you can get the idea of what bootlock does. The function allocates a contiguous physical memory. Simply, it gets an argument n as the size of the memory that it should allocate, and if n is bigger than 0, the function allocates a contiguous physical memory in page granularity. You do not need to initialize the content of the memory, and another requirement is that you need to return a kernel virtual address of the corresponding physical memory. And if n is 0, then it returns the address of the next free page without allocating anything. Additionally, if the system is out of memory, then you need to call panic as a function. For the next, let's take a look at how we can implement bootlock. In the code, you can identify that there is a pointer variable nextfree. And the variable is to point the start of the unused physical memory so that JAWS can allocate a contiguous physical memory starting from that address. And at the initialization step, the code sets nextfree by rounding up the address of the variable end in page size. And this variable end here is a special variable, and our compiler inserts the variable exactly at the end of the kernel. So after our bootloader loads the kernel, because the end points to the end of the kernel, we can safely assume that all the physical memory address above the address of the end will be free. So we set the address of the next free by rounding up the address of end in page granularity, because we need to allocate the memory page by page. And in bootlock, we will maintain a one invariant. That is, the physical memory region at above next free should be free. Please make sure that we need to keep this invariant within this function. And next is about taking a look at the example of how actual memory allocation should happen with bootlock. Suppose we have a request for allocating 16 kilobyte of memory. In such a case, what we can do is set a new variable, new nextfree, as the roundup of the nextfree plus 16 kilobyte to point the end of the 16 kilobyte memory if we allocate a new one, starting from the nextfree. Additionally, we create a new variable, pre-nextfree, to point the previous location of the nextfree. And then we can update the nextfree to this new nextfree. Like this. So we can keep the invariant. Anything above nextfree is free. Next, again, suppose we need to allocate the 32 kilobyte of memory. Then, in such a case, we set the prev nextfree as the previous nextfree, and then set the new nextfree as a roundup of nextfree plus 32 kilobyte, and then we will return this previous prev nextfree, and before that, we will update the nextfree to prev nextfree. And no, nextfree to new nextfree, like this. By doing this, we can keep the invariant. Anything above nextfree is free. In doing this, some of you might be curious how we can maintain the value in the variable nextfree, because the variable is defined within the function. However, the variable is with a type qualifier static, and what it means is that the variable is not a local variable but a global variable. But it's a special global variable, so you can regard a static variable within a function as a global variable that can only be accessible within this function. So you can regard nextfree as a global variable, but in the scope of the outside of this function, you cannot access this nextfree variable. But within this boot_alloc function, you can access nextfree, but you can regard this as a global variable. So across the multiple function calls, the value of the nextfree will be maintained, and then it will not get reset because this is not a local variable but static variable, and function means global variable. And in case if you don't know all the meanings of the static static keyword static in C and C++, and I will let you know about 3 different meaning of the keyword. The first usage is, as we just said, to indicate a global variable within a function. And the second usage is a function or variable within a file. For example, this function, boot_alloc, is with the qualifier static, so this function can only be accessible from this file, current pmap.c, but not from any other files. Finally, the third usage of static keyword static is in C++, and we use that keyword to refer to class static functions and variables. So these are all 3 meanings of the static. Next is about implementing meminit. Before starting, please remove the panic line in the code as shown in below. After that, carefully read about the commands in the code to figure out what you need to do. And from the description on the slide, you can catch that we need to allocate an array struct page info for the number, like end page numbers. the number of physical pages in memory, and then we need to initialize all the field of each struct to 0. More accurately, you need to allocate the memory for the variable pages, which is an array of struct page info. And the reason for doing this is that we will keep track of free physical pages, and we will do this by using this array, an array of struct page info. And we will need to allocate one struct page info per each physical page. So some hints for meminit are: you can use bootalloc to allocate memory for the variable pages, but you should know the size argument that you need to supply to the bootalloc. And to get the size of the allocation, you can get the size of the struct page info by writing the size of struct page info, and you need to allocate that for the number of total physical pages, and the JOS will automatically store the value of the total number of the physical pages in the variable n pages. So in that case, by multiplying n pages to the size of the struct page info, you can get the memory size that you need to allocate using bootalloc. After running bootalloc, you can initialize all the elements and the fields of the array by running memset to pages for the allocated size with value 0. And then, next, how JOS manages free physical memory. You can regard struct page info represent the status of the physical memory page. So that's why we need to create one object of struct page info per each physical memory page. And because right now our JOS uses like a 128 megabyte of memory, so we need to allocate 32,768 entries of the struct page info. So you can easily get the size of the memory that you need to allocate by multiplying this number with the size of a struct page info. But you can get the size of the struct page info in the code via size of the function, and also you can get the number of the total physical memory pages from the variable n pages. And we will manage such entries by having a linked list starting from the variable page free list. And we will link all free physical pages and maintain the corresponding struct page info as a linked list. And in other words, we will create a linked list of the struct page info for free physical memory pages, and whenever we allocate a page, we will remove corresponding struct page info from the list because they are not free. So the variable pp_link is there in the struct page info, and it is typed itself as a pointer. And this is for creating the linked list to point the next page info object. So starting from the variable page free list, the variable will serve as the head of the list, and we need to link all free physical pages by attaching objects using the variable pp_link. And then, how to build a linked list in C. So for those of you who never implemented a linked list in C, I would like to give a brief introduction for building one with very few lines of code. So to finish lab 2 about the memlayout, first you can set the variable page_free_list as null. And after setting the ppRef, which is a variable for counting the number of references to the corresponding physical page. So to set the reference, like a reference counter, ppRef, please follow the guideline written in the code as comments, and also take a look at our descriptions, lab assignment descriptions on the website. And then you can run the following loop, having a for loop over the entire entry is in the pages array. And if the ppRef of the item is 0, which means there's no corresponding, which means that there is no reference, which is the corresponding physical page is free. Then we attach the control list. Control list head is page free list as the tail of the current object and switch the head to this new object. To visualize it, let's take a look at starting with the null for the page free list. And whenever we see a free page, we link the current head as the tail of the new free page, and then at this line, switch the head to the new struct object. Then, now our list look like this, and whenever we see a new free page, link the current head as the tail of the new object and switch the head. Now the list has two elements like this, and by keeping doing this with the loop, you can build a linked list starting from page free list, next free page, next free page, next free page, and on and on and on. And at the end, you will see the null pointer. And about ppRef variable in struct page info, and the variable exists to count the number of references. In other words, the variable is there for indicating the number of uses of the corresponding physical pages. So we need to assign the value 0 to this variable if the corresponding physical page is free, and whenever we use the page, we will increment this variable to count the number of uses of the corresponding physical page, and having non-zero value in ppRef means the page is not free. So in page init function, you need to set the ppRef of all struct page info, either 0 or 1, by following the instructions in the code and comments, and then you need to build the linked list for free physical pages. So if you get lost, please come back to this video or lecture tutorial slides and get a clear idea about implementing the page init. After building the list, allocating a page can operate as follows. To allocate a new physical page, you need to get a physical page, a free physical page. To do this, you can cut the head of the list, head of the page free list, and move to the next element and use the previous head as the new page, that will be allocated. And the function page alloc need to handle this functionality. And in exercise 4, when you use the page alloc, you need to assign corresponding PDE and PTE to create entries to enabling virtual to physical mapping. And then you need to increment the pp_rep by 1, marking that we just added one more usage to the corresponding physical page. But please do not do this within page alloc. You need to do that when you use this page alloc. And to release a page, which is an inverse operation of allocation, you need to decrement the pp_rep by 1 because we just released one use of the physical page. And then if the value of the pp_rep becomes 0, that means there is no usage anymore. Then we need to put the page, the struct page info, back to the page free list. So in allocation, we cut the head and move head to the next and use the like a previous head for the free page. And when we release the page, we need to decrement the pp_rep by 1, and if it becomes 0, then we need to put this page back to the page free list. And this is what page free function need to do. And up to this point, I described briefly about how you can implement each of 5 functions in Lab 2, Exercise 1. And for the next, I listed some tips for you for some of the macros and some information about the types and casting that you can utilize a lot during finishing Lab 2. So please read about each macro and its description, and also each items of the type and casting, and use them wisely. And I believe that you might want to come back to refer to some of the macros and some of the type informations during finishing Lab 2.